Welcome to my poster, Multiscale Modeling of Charge Dynamics in Neuromorphic Device. Neuromorphic devices have been used for massively parallel information processing. A large part of this device is based on electronic materials, in which ion, electrons, and holes are both available in the materials channel. This device relies on ions to be injected from an electrolyte on the top of the channel to change its doping state and conductance. This is achieved by applying voltage pulse on the gates, which control the injection of ions into the channel. Figure 1 demonstrates the mechanism of neuromorphic device. The type of reaction process depends on the circuit mode. However, it is largely unknown how the device operation is related to the microscopic processes. In our research, charge dynamics in neuromorphic device is studied using a multiscale approach combining molecular dynamics, density functional theory, and kinetic Monte Carlo. Master equation is used to study the charge dynamical behavior, and graph decomposition method is developed to analyze the connectivity of the dynamics network. To this end, our research objectives include implement multiscale approach to model charge dynamics, investigate the electric field's effect on charge dynamics. Later, we quantify the effects of model uncertainty and use the perturbation method to study equilibrium and stationary distribution. The process of multiscale modeling is outlined in Figure 2. Molecular dynamics simulation is performed to sample device morphology, which are partitioned into segments corresponding to a single neuron in the device. Electronic coupling between segment pair is calculated by DFT. The psi energy is attained through QMML method, in which the segment is treated in quantum level by DFT. From electronic coupling elements and psi energy, one can calculate the transition rates, based on which KMC and master equation models are built. Computational details are given. Classical MD is achieved by LAMS using gauge force field. The DFT is performed using OCA, and QMML method is implemented in VOCA using long-range embedding with atomistic polarization. From classical MD morphology, the ion distribution around p dot is described by radial distribution function in Figure 3. In the electric field environment, chloride ions are clustering close to p dot, while sodium ions are at a further distance. The spatially resolved energy levels in Figure 4 shows that electric field contributes to a higher HOMO level. The spatial correlation of HOMOs in Figure 5 suggests that within fluctuations, the HOMOs are more correlated in electric field. Graph decomposition algorithm is developed to study the connectivity of the segments. In this model, the Jacobian matrix of charge dynamics is represented as weighted graph. Figure 6 plots the eigenvalues of graph normalized Laplacian matrix. For eigenvalues smaller than 1, the larger magnitude indicates stronger connectivity. Figure 6 suggests that the segment network is more connected with electric field. To guide interpretation of how eigenvalue measures connectivity, we study the graph Laplacian matrix of 1D lattice, which only has Lewis side connection as shown in Figure 7a. All the fast jumping rays are equal to 100 with 2 slow rays m equals 2. We place the slow rays at various positions. Figure 7b shows that the Laplacian matrix sequence modulates eigenvalue as a function of the slow rays position. When m is at 1 or 200, the graph is strongly connected. The eigenvalue is in the magnitude of 10 to -4. So in conclusion, when electric field drives chloride ions close to p dot, the device is at a higher HOMO level and becomes more spatially correlated. The eigenvalues of the graph Laplacian suggest that the segment network is more correlated in electric field. The next research step is to implement master equation to verify the fast or slow dynamics with the input of voltage.